So this problem is pretty easy. It says how much work must be done by frictional forces in slowing a 1000 kilogram car that is going 26 meters per second to rest or zero. So one thing we should know is that the work is going to be equal to the force of the friction times the displacement, in this case delta S. In this problem, the force that is going to stop the car and it's going to make it to be at rest or velocity equals zero, it's going to be in the opposite direction as the displacement. So they're going to be opposite. That means that the work that is being done has to be negative. So we can also write the work being equals to the change of kinetic energy, or the kinetic energy of the final time minus kinetic energy initial. As we know that the final kinetic energy is going to be zero at rest, we just have negative 1/2 the mass times velocity squared. Then we have to plug in the values. We have negative 1/2 times 1000 times 26.1 squared, and that should give us around 340,605. But then for the answer, in letter A, it's written in scientific notation. So our answer would be 3.41 times 10 to the 5th joules. Being that the force required to slow the car of 1000 kilos to be at rest at velocity zero. So in this problem, they're giving us that there's a 10 kilogram block on a table that is connected by string to a 63 kilogram mass, which is hanging over the edge of the table. Now, assuming that the frictional forces may be neglected, they're asking us about the magnitude of the acceleration of this mass of 10 kilograms when the other block is released. So what we're gonna do is break it down into pieces, and we're gonna find the sum of the forces of one mass, the 10 kilograms, and then the other mass, 63 kilograms. So in regards with the mass of 10 kilograms, we only have a force that is going to its right. Therefore, we could say that the sum of all the forces in the x direction, which is the only direction that is going to have a force, is going to be mass times acceleration of x. So t is going to be equal to mass times acceleration, but we only know the acceleration, only the mass, so it's going to be t equals 10a. In the second part of the problem, we're gonna look at the second block, the 63 kilograms. So I just drew it right here. We have a tension going up and we have the weight going downwards, mg. So if we choose the acceleration to go downwards, that means that the weight is going to be positive and the tension is going to be in the opposite direction, is going to be negative. So if we do the sum of all the forces in the y direction equal to may, we can replace that sum of all the forces to the weights minus the tension being equals to ma. As we plug in values, the 63 kilograms times g, which is 10, we then subtract 10a, which is the value of t that we found in the first part. Then we just continue solving the problem, and we find that a is going to be 630 over 73, which is the same as 8.6 meters per second squared. So our answer would be letter A, which is 8.5, and that's pretty much close to 8.6. That's the final answer.